All right. Hello, everyone. Good morning. Thank you for being here. I'm excited to be here, and I'd like to thank the committee for putting together such a great event so far. Looking forward to the rest of the talks today and tomorrow as well. I'm Luis Rodriguez. I work for the Johns Hopkins Applied Physics Lab, and I am one of the flight software engineers that got to work on the DART mission. And I am here just as a representative, really, for a much bigger team that did some great work. But I just got lucky and get to present to you all. So I do have a lot of information because DART is really exciting, and I wanted to just do an information dump. And so it may appear as if my talk is faster than real time. So we'll see how that goes. All right, so quickly, just we'll go through a DART mission overview. We'll look at the hardware architecture and the flight architecture, and then we'll talk about some of the more specific DART CFE applications that I thought would be exciting to share with you all. And then we'll talk about some mission ops and results because it's always cool to see, spacecraft hitting a rock. So, all right. So real quick, the DART launch happened on November 24th of 2021 on top of a SpaceX Falcon 9 in Vandenberg Air Force Base out of California. And so the target was a binary system, the Didymos system, which is composed of a large asteroid called Didymos and a smaller asteroid called Dimorphos. And the idea was to hit the smaller asteroid. We weren't trying to make our lives more difficult by hitting the smaller one. We were actually trying to make it easier by being able to more accurately measure the success rate, the impact that the actual mission could have by measuring the change in the orbital period of the smaller asteroid Dimorphos around the bigger asteroid Didymos. So impact occurred relatively recently on September 26th of 2022, and it happened around 7:14 p.m. Eastern time. But because our engineering team and our science team has been working on exactly detailing all this information, we can actually tell you that it happened on 2022, 2609, 2314, 24 with 0.183 plus or minus 0.004 seconds. So, yeah. So the impact happened 6.8 million miles from Earth, and the way that we observed it was two different ways: through ground observations as well as through Lisha Cube, which there was a great talk yesterday from the Lisha Cube team, and those took some great photos that I'll be sharing as well. So in order to accomplish the mission, there were certain technologies that DART kind of implemented, because DART wasn't only a technology demonstrator at the planetary defense level, but also at multifaceted level. So testing the smart navigation system, which is what actually guided us towards the asteroid within that last couple of hours of the terminal phase of the mission towards the asteroid. The Draco telescope, which took those great images. The Nexi ion engine from NASA. Rollout solar arrays, or ROSA, which had been flown on the ISS before, but now they were the primary source of power for the DART spacecraft, and a critical component. The Lisha Cube, which flew with us, the radio line slot array, which was just a high gain antenna that we were able to use in DART so that we could downlink some of those great images that are roughly under a second, to kind of see the impact firsthand here on Earth. And then the CoreSat avionics, which is what we're going to be focusing on a little bit in the next couple of slides. All right, so what is the DART flight software architecture? We were running flight software on a Leon UT700 running at 100 megahertz. And then on top of that, that UT700 was talking to an FPGA that we call DRIP, the Draco Image Processor, which is at Leon 3 operating at 30 megahertz. And then on top of that, we had a set of different resources. We had two SRAM banks of 16 megabytes each, one for the flight software image and one for the Draco image processor, where a lot of the intense Draco image processing was taking place. And then we had 8 megabytes of MRAM for flight software, of which we consumed roughly 4 megabytes. And then we had 8 gigabytes of flash, again, twofold, one for the flight software image and one for the Draco processor. So most of the traffic from flight software flowed through a SpaceWire router And I say most because there was also the flow to the actual Draco image processor. But from the SpaceWire router, we had a couple of different avionics components, or what composed the processor module. And that was obviously the SPC, where flight software is running, the spacecraft interface card, the thruster actuation card, and then the mission specific card. Um, so lots of acronyms that I tried to list there as to the way that from the SpaceWire router to these avionics cards, we were talking to the rest of the sensors and things like that to get telemetry flowing, and also feed our guidance. Oops, sorry, our guidance and control models based on things like the IMU state and star tracker, and being able to actuate the thrusters and things like that. So in order to communicate with all this hardware, we had a set of different applications. A lot of them are actually just part of the CFE core, right? Like we're familiar there with like CI and TO. So I won't go over some of those, but the bold ones I think are interesting. First of all, the SpaceWire router interface app that kind of acted kind of like a data trunk where all of the data, all of the applications communicated or used a SpaceWire lookup table within the SpaceWire application to find their way to the specific card that they needed to talk to. And so that was our first, SpaceWire app. Then we had an imager application which talked to the Draco instrument and the Draco image processor. We had DCIU, or the digital interface unit control unit, and that talked to the Nexi engine, which I forgot to mention earlier. Nexi, the Ion engine, was not a critical component for mission success. It was only a technology demonstration, so we actually had, the thrusters that we guided ourselves with towards the asteroid were not the Nexi engine. We had our guidance and control wrapper, our IFM interface module application, radio, and MSN. And then just to draw a quick reference to the instrument telemetry manager, which was this external kind of application that facilitated communication between the Draco image processor and the flight software. So it was kind of an in-between application that allowed for the flow of commanding and telemetry from the processor over to the UT700, and it also allowed for some of that image flow that we'll talk about in just a second. So quickly diving into some of the applications, and I'll try to go through these quickly. IFM was pretty much our application to talk to all the different avionics cards, mainly the SCIF and the TAC, and get some information on the PDU, PSC, and reuse, power distribution unit, power switching unit. And then the MSN application on the other side was just more of your standard application on collecting information on the SBC. So like things like ADC channels, how much current we're consuming, that kind of stuff. And then also reporting a flight software version to, keep track of what exactly you're flying. On the radio side, we actually were flying a Radio Frontiers, a Frontier radio that was developed at APL and uses a very interesting kind of ICD called a radio personality. And so the idea behind this radio is that from a flight software perspective, we're just kind of working as a bent pipe. We don't really have to look at any of the contents of the message. We're told a specific mission mode that the radio would like to be configured to, and then we ship that over to the radio, and the radio interprets that mission mode to set up a set of presets, right, that set the downlink rate and a couple of other things like whether there's a subcarrier lock and things like that within the radio. So that worked for both commanding and telemetry. From a telemetry perspective, they just sent us a telemetry packet. We downlinked it. It's pretty much standard for everybody. And the radio application, something I just kind of wanted to allude to, is that it didn't really handle, kind of as a misnomer, didn't really handle downlink and uplink frames. This is specific radio commanding, right? So once an uplink frame had gone up to the command ingest, through the command ingest application, and had been identified as a command to the radio, then this application would come in to ship that over to the radio via our SpaceWire router. The DCIU application was a really cool one too. This is what allowed us to talk to the Nexi engine via the PPU, which is the power processing unit. And the idea is that you can talk to the power processing unit, and by offsetting some of these voltages and currents, you would subsequently control the thruster itself. And what's really cool about this is that it's not a single one, like fire the thruster now or ramp up the thruster now. It was a multi-step process that needed to occur to successfully carry out those objectives. And so the DCIO application actually implemented an internal finite state machine that stepped through each one of those configuration steps and then either exited if it found an error during the configuration phase, or it retried some of the steps. So I could go into a lot of detail about the finite state machine, but we're already going faster than real time. So I'm going to go on and move over to the imager application, which is the one that controls the Dart image pipeline essentially. So this is imagers controlling Draco, and it, like I have said, it's composed of DRIP and the Draco instrument itself, which is connected to an FPE, which is a focal plane electronics, and that's just what's actually handling the data interface to the rest of the avionics components. So to walk you real quick through how the image pipeline worked, on number one there, the image is taken, that gets handed over to it's a kind of composite between the telescope and the actual detector. That hands the data over to the focal plane electronics, which then via SerDes link, if we're talking about image data, the SerDes link gets used to send that data over to the Draco image processor, which is number 4 there. And then it has the capability via flight software commanding to either save images to that Draco flash that we talked about, or just stream the images straight down to the ground. And that's the recording is really more what we did for OpNavs during the mission, and to do some Jovian moon testing to kind of test out the SmartNav algorithm. But the streaming is more of what we did in terminal, right? Because we can't really record it, because when are you going to play it back? Hopefully. So for the streaming, it would go, the image data that would then go to the RIA up there, which is the radio interface adapter. And this just practically kind of applied a ratio of how much flight software data to image data do you want to downlink, so that you can get some state on some status information on the flight software, while also downlinking these relatively quickly generated 512 by 512 images. So the imager application, in order to achieve that, in order to kind of communicate with the FPE and DRIP, it also implemented a state machine. And the reason why I needed to do that is because, for example, for the detector, it was interesting in that it had a register space within the focal plane electronics, and then after you loaded a set of configurations to that register space, you needed to tell the FPE to go ahead and implement or copy those registers over to a detector register space that was not accessible by us by flight software, and then those instructions would then take place, and the detector would actually be reconfigured to change the gain or change the integration time of the detector. So in order to ensure that you're not kind of misconfiguring the focal plane electronic register space and then telling the detector to use that, and then getting really messed up images or into some bad state, we implemented another state machine, right? That is now going to configure the register space, verify the register space, and after that, it'll tell the detector to go ahead and start using those configuration settings. The Draco image processor was similar in that it wasn't so much the configuration step that needed multifaceted, a state machine. It was actually the boot process. And the reason why we needed to reboot DRIP is because the ITM image, which we talked about before, and some of the other components like the bad block table for flash and a calibration table that we'll discuss soon, it was in a piece of SRAM that wasn't really radiation protected, and so we knew that there were going to be some offsets. And so what we wanted to do was just every time that we were going to rerun or use DRIP actively, we would kind of reboot everything to get a fresh start. And it was really interesting because actually through the mission, there's this 1 megabyte calibration table that's pretty much used to, when you take a picture of whatever you're taking, the calibration table is used to subtract values that are noise being introduced by the detector itself at different temperature ranges. And so we actually saw that over time that cal table CRC would change. So it was good that we were, every time we wanted to use it, we would reboot DRIP. So from a focal plane electronics perspective, There was a power on and power off sequence where we kind of sat at idle, and then if we were told to do something, we would exit that idle state, go do some sort of operation. More interesting, little in that middle column where the begin configure step is, you can see how there's like multiple steps to this process, right? We can load registers to the FPE, verify them, and if we find a failure, we would actually either retry the load or just exit out and report that, so that from the ground we could react. Um, and then after if all the steps are successful, then you have successfully configured the detector. But you can see how there's it's interesting because each one of these operations happen on a 1 hertz tick. So it was like each step was happening on 1 second. So right there you can tell that's 2, 4, 6, 7 seconds, right? Roughly 7 seconds that it would take you to configure the detector. And that was some of the fun stuff that we had to deal with during operations, kind of figuring out, if they were we were kind of told it is not going to be a real constraint to have to reconfigure the detector, but just because you're told that it's not going to be a constraint doesn't mean it won't become a constraint. And so it did. And so it was fun to kind of try to pinpoint exactly that configuration latency, I guess. From a drip perspective, similar thing. I won't dwell too much here, but essentially, what's really interesting about the drip side is that it wasn't only because it's on the boot side and you're kind of copying all this memory from the flight software RAM space, or I guess essentially NVM. But eventually, when you're actually doing the copy, you're copying from the flight software RAM space over to the Draco SRAM space. Um, there were these really big memory chunks that we needed to copy. There was a calibration table that was like rough. I put 1 megabyte there, but it was roughly 2 megabytes. I guess I was just wishful thinking. And then the Leon image, 128 kilobytes, bad block table, 1 kilobyte. Um, and so we needed to make all these copies every single time that we booted drip. And in order to do that, we implemented a little child task, not so little, that then would do the copies of those big memory segments from flight software over to the Draco SRAM space in 1 kilobyte blocks. And that was mostly event driven. That wasn't like 1 hertz, because that would have taken a while. So but it was a low rate task, meaning that we would consume as much of the CPU as was available, but we were always kind of punted lower down if a more critical operation was happening. And so that meant that CPU use had a direct correlation to how fast we could boot drip. And again, that wasn't a constraint when we launched, right? But then it quickly became why isn't it, why can't we just boot faster? So um, there were 3 different boot sequences to kind of account for the fact that these boot sequences were going to take so long. We had a soft boot that took about 6 seconds. We had a medium boot that took about 33 seconds, and that only loaded the Leon image, which is just the ITM image, and then the bad block table. And then a hard boot, which took about 127 seconds. And that was the more ritualized one when we were actually in the mission. So we kind of put together this rough graph of like, okay, depending on an average CPU, how much would it take? And you can see that we were able to at some point test with like a 90, I think we reached 98% CPU, just trying to drive flight software as unrealistically as possible to get it up to that 98%. And then we could see that we were taking about 450 seconds to boot drip if we loaded the cal table. And so fortunately, none of that really became a concern, because during the mission and through most of the mission, even in the most rigorous parts like terminal, we were operating at around 80% CPU, so we had a 20% margin, and that was a pretty consistent 130-second boot time for the Draco image processor. All right, so the next application was GC. This operated on 100 hertz and 10 hertz tasks, and I have there that it wrapped the GNC algorithms, but something I failed to mention in the slide is it's also handling communications to the IMU, the sun sensor electronics. So it's doing a lot more of that interface handling so that we can feed that sensor information over the GNC. I also put there an image on the lower side of how the image processing on the Draco side worked with the GNC algorithms themselves. So a Draco image would be taken. That's the white box there, and then there would be detection blobbing and centroiding. So what the Draco image processor is trying to do is kind of, and it's cool because I saw during the Lisha Cube talk, a similar process, but kind of try and change the using a threshold number, changing how the image appears to the Draco image processor, so that then it can do some blobbing and then find a centroid to that blob, and then it would report those centroids out to the GNC algorithm. And we could have drip, depending on configuration, report either 16, 32, or 64 centroids. We never saw a need to report more than the 16, but we did have that option. And so that line there from targeting, or sorry, from centroiding over to targeting, that was the FPGA kind of passing 16 centroids over to the UT700. And then from there, the guidance filter and targeting would do all the magic to figure out exactly which of these centroids are the most interesting to us and which ones do we have fair confidence in being either Didymos A or Didymos B. And then it would assign a label, a track label to that centroid. And that's how it kind of figured out, I've seen this centroid in multiple images, so I have fair confidence that this is an actual body I'm seeing, rather than this is a centroid that popped in and out of a frame. It may just be noise, right? So, and we tried to filter out a lot of that noise by configuring the Draco image processor to different settings, so that you can kind of flush out everything except for the two main bodies based on the albedo and like the brightness that we expect the Dynamo system to have. But you still get, random flashes of radiation that are actually really cool to see, but not super useful. And so, yeah, that was pretty cool. All right, from just mission results and kind of things like that, I want to bring it back to that calibration table real quick, because the calibration table, unlike all of the other things that we had to configure Draco to do, was actually stored in, it was compiled into flight software. So that whole thing was not a parameter that we could just upload, or a file that we could upload into SSR and then copy out. It was actually compiled into the code. And it was statically allocated in the code, which gave us the opportunity to kind of telemeter down where exactly in the RAM space the beginning address of the cal table was. And if we ever needed to patch it, we could kind of patch it from that address over to like the full extent of the image. But the reason why we decided to do this, which sounds a little bit unconventional, is because guess what? We were kind of told, it's very unlikely we really understand the detector. I don't think we're going to really need to upload the cal table during the mission. And guess what? We needed to upload the cal table during the mission. And so that was honestly very fun from a flight software perspective, because I think we put all the tools there to do it, and we just thought we were never going to be able to implement it. And then it came inconvenient. So this cal table being so large took about 3 hours to load. But what we did is kind of like what you do with a flight software image patch, where you take the difference between the two cal tables and then you just upload, word aligned segments of the image, and that reduced it to I think like a 40-minute total. But that included not only the load, that included like the verifications before and after. So it was a 40-minute operation at that point. So yeah, so that was a pretty fun one. All right, the next thing I wanted to do was kind of take you into the mock on terminal day, right? And this is what most of the engineering team, mostly, like I think everybody had this display open because it's a cool display. But really, I think a lot of the Draco team, flight software team involved with the imagery application, things like that, were looking at it for, kind of making sure that the system looked good. But what you're seeing on the top left there over here is our centroid view. And this is just where within the field of view, so the field of view of Draco is 1024 by 1024 pixels. Within that, there's a 512 by 512 region of interest, or ROI. And that gets updated by the GNC algorithm depending on where it believes that the DART system is. And so I'll go ahead and click. Oh. Maybe I need to exit the laser pointer. Yeah. So you can see on the top left how that little region of interest, or ROI, is bouncing around the field of view. And it already has a label on it. It has label A. That means that the GNC has identified that as a viable track for Didymos based on an array of different parameters. And so on the right under that, what you see is the size of the blob that the Draco image processor is reporting, and how that correlated, or how that matched to the theoretical analysis that we had done based on Didymos. So we were pretty excited at this point when we saw that it was kind of nailing right in the middle, right? we kept kind of asking the person, the SmartNav algorithm folks, do we need to change any of the Draco image processor? Because we had a bunch of contingency procedures to kind of implement if we needed to change anything. And they kept saying, nope, we're right on the money. So from an engineering and just science and Dart enthusiast, I was really excited. From a person that was heavily involved with all the contingency planning, I was like, come on, let me reconfigure once, just once. But on the middle there, you see a list of centroids, and that is how the 16 centroids. You can see there's 16 of them, right? Like we were talking, and you can see that there's 2 centroids most of the time, but it starts just ramping up, and you can see that we start reporting a ton of different centroids as we're getting closer to the asteroid. And the video actually ends 2 minutes and 30 seconds prior to impact, as you can see there. And the reason for that is because at 2 minutes and 30 seconds, we shut off the SmartNav algorithm. At that point, I got too excited. At that point, we're cruising, right? We're no longer actuating any thrusters or anything. We're just cruising straight at the asteroid and trying to keep attitude, but we are not thrusting anymore. And so that's why all the SmartNav kind of shuts off. What's really interesting is if you compare this to the actual image of the video, what I'm showing there is on the left is the image that everyone saw on impact day, but with an overlay of what the SmartNav system was kind of looking at. So in purple is Didymos, in green is Dimorphos. In the middle right there before it disappeared, what you could see was a zoom in of each one of those bodies. And then I'm actually not going to give you the satisfaction of looking at the impact just yet, because what I want to point out is if you actually kind of jump around in the video, and we can jump okay, maybe I'll just let it play and tell you to keep an eye for the amount of centroids that are getting reported on the edge of that right image. You can see that because we're applying a DN threshold and we're kind of saturating the image so that the centroid can't pop out. We're actually creating different blobs, right? And these are getting marked as different centroids that the algorithm is being told you should be aware of. But because we had already precision locked at that point, meaning we had decided that we knew where Dimorphos was, we kind of ignored those other centroids being reported. Now you get the satisfaction seeing the impact, both on the left as Draco saw it and on the right as the Draco image processor was seeing it. So we impacted again at 7:14, and that was we expected originally to change the orbital period by 7 minutes if successful, but we actually were like all the way on 33 minutes. And the reason for that is because we actually saw a lot more ejecta than the scientists were originally thinking that we would see. So that was very exciting. And an epic image that the Lisha team captured was that one right there. And it's one of the most beautiful images that every time I hear talk about Dart, we got to impact the thing, but we're really glad that Lisha Cube was there to take a close-up of it. So what's really cool is that the whole world kind of stopped for a second and looked up, and that did not include only people here on the ground, like from the project, from the University of Hawaii and people around the globe, really, but also James Webb and Hubble were taking pictures of the impact, which is really exciting because in the mock, all we were seeing was Draco, and then we started going on Twitter and everything was blowing up with like different posts, and every 5 minutes was a different post, so that was very exciting. Some recent analysis, and I'm running low on time here, but some recent analysis that was just published in a Nature article, actually, that I encourage you all to go check out, is the science team and engineering team have kind of come together to kind of put these things together, and we can see exactly where Dart impacted. You can see there on the top image how where exactly Dart impacted the asteroid, and the fact that it landed, the bus of the spacecraft landed right between those 2 boulders, which ripped to those 2 boulders. And then right underneath it is the impact angle, which shows that it looks like our plus Y solar array was the first one to kind of hit boulder 1. Then the negative Y array graced boulder 2, and then the bus just full on slammed against the middle of the 2, and that's where most of the momentum transfer happened, since the bus is really like 88% of the total mass of the spacecraft. So then the plume comes out, right? You get all those cool images, and yeah, we were able to successfully do that. So I think I'll finish it there, and thank you all. And they can't be so sure anymore. So that's it. Thank you.
All right, we have 2 questions online. The first is, what version of CFE did you use, and will your CFS apps be available on GitHub?
I can answer the second one. No, they will not be available on GitHub, at least to my knowledge. As far as what version of CFS, I'm actually not sure off the top of my head, but I'm getting 1.5, 1.5, 6.5. Okay, 6.5. Yeah.
We'll do one more online before we go in person. What software did you use for the mission control display in the animation?
Oh yeah, that was in Control's J display, and it allows you to do a lot of cool stuff. I mean, it's an interesting tool to work with for sure, but you do have a lot of flexibility over the kinds of things that you can successfully display. So, yeah.
Okay, in the room.
Awesome talk. Thank you very much. So I'm more on the guidance and control side of things, and I was curious about the team's decision to essentially design the controllers and stuff in MATLAB Simulink and then auto-code it. Obviously easier for the control engineers, but then you end up with more technical debt, I guess, later on in the project. So I'm curious about the trade-off there, and if you have any comments, because I know that's it's a common practice in a lot of companies. So
Yeah, it is a common practice. I feel like because it is a common practice, when the GNC team makes a drop, it is kind of it raises a wave of things that then you gotta kind of respond to. But I think our team is pretty used to it, and I don't think that it was really considered that big of an issue. In terms of the flexibility that allows, I think it's really powerful, right? Because they get to run a lot of standalone simulations on Simulink and things like that, for which they already have all that infrastructure. So I think the toll that the flight software team has to pay may not be worth it. And I'm looking at my flight software team folks to see how they feel about that. But yeah, that's what at least my limited experience working with the GNC team has shown me.
thanks.
All right, and one last question in the room.
So I saw you talked about patching the Draco image mask of some sort, and you said that you stored it in RAM. Is there a reason you kept it in RAM as opposed to writing it to NAND or some non-volatile memory?
Yeah, well, so it was part of the flight software image. It was technically part of NVM. It's just that when we decided that we needed to patch the flight software, we decided to only patch it in RAM because the cal table differences weren't. We had a set of different Draco parameters that we could configure to account for the old cal table. So we were okay that if there was ever a processor module reset or anything, we would just default back to the old cal table and use that one. But actually, I'm glad you brought that up because I did want to mention that flight software did not have to patch flight software at all during the mission. There was only one processor module reset throughout the whole thing, and it happened due to a non-flight software issue. But yeah, so it was exciting that at least we got to do that, I guess, from a mission perspective.
It's awesome. Thank you.
Yep, no problem.
All right, let's thank our speaker. Thank you, Louis. All right.